I'm Franziska. I'm a research scientist at Facebook AI Research, and my research interests are broadly at the intersection of machine learning and robotics. Um, and really, mostly, I'm focused on manipulation. When I think about what I want our robots to be able to do, I come up with all of these examples of um, us humans doing some cooking, some cleaning, watering the plants, repairing some equipment. And one of the things that I really notice is that we humans are easily able to perform many, many skills with infinitely many variations. And what I mean by variations is just that, once we've learned to water one plant, it's easy for us to water another plant. It's not a big deal. And most of the robotics community is still focused on learning one set of skills or one task family of skills. And what I'm really interested in is understanding what representations we can learn that enable fast learning of new skills or adaptation to novel settings. And really, what I'm going to talk about in this talk is what representations can we learn that help us adapt to novel settings fast. So what does it mean to learn to adapt? Well, let's look at this supervised learning problem here, where we have some input X and want to predict some targets Y. This model is parameterized by omega, and we really want to learn these parameters omega. What we do these days is that we have some loss function that measures how well we're doing in predicting the targets Y, and then we back propagate that loss to update parameters omega. And to execute this learning loop, we need to define a loss function, some optimizer, we need to choose a learning rate, and we also need to initialize our model somehow. And all of these are actually learnable. And in fact, all of these have been learned recently. So this concept that I'm talking about here is meta learning. And this has become very popular recently. And while I'm going to highlight a few related work right now, I won't be able to give a comprehensive overview. But if you're interested in a comprehensive overview, there is a recent survey on meta-learning in neural networks. But to highlight a few examples, so MAML has become very popular for meta-learning a model initialization. So what MAML learns is some initial parameter omega that allows for fast adaptation to novel settings. Then some of my prior work was concerned with learning rates that help to adapt faster to errors made. Then other related work is about learning the full optimizer. And then some of our recent work is concerned with learning of loss functions. And just to give you a quick overview of how I think of the pros and cons of these methods is that really these three methods are somewhat tied to the model architecture, right? The model initialization depends on the model architecture. The learning rate, if you only learn one learning rate, then not so much, but if you're trying to learn the learning rate for all layers or all weights, then you also tied to the model architecture. Optimizer is somewhat similar to this, the learning rate issue. And then with the loss function, you actually don't have this issue at all because it's completely independent of the model architecture. In fact, some of our recent work shows that we can switch out architectures and still achieve a good performance after learning loss function. Okay, so, but this is as much as I will go into the details of the pros and cons of different meta-learning methods. What I really want to get to is, how can this help us in robotics? And yeah, as I've just mentioned, I'm going to focus on the learning of loss functions for the rest of the talk. Okay, so what I decided to do for this talk is to really focus on one example that we also have some results for, and just walk this through from beginning to start, also from a robotics perspective, which hopefully helps this community with understanding some of the intricacies of learning for control. The example that I'm going to focus on is a pick and place example. And now just imagine you have the shelf here with all kinds of objects, and you want your robot to put a subset of these objects onto a table, or imagine the reverse. You want your robot to, clear things off the table and put them back on the shelf. Okay, so putting each object back is a, let's say, a pick and place task, and really we should be able to specify this with one policy. When I talk about a policy here today, what I really mean is just something that takes in state and goal and gives us an action sequence. I'm going to just assume for this talk that this is all open loop, in the sense that it gives us a full trajectory of actions that we want to traverse, that we want to execute and achieve. But whatever I'm talking about today also holds for closed loop policies. Okay, so this policy, what I'm talking about right now, it could be a policy learned via model-free reinforcement learning. It could be a policy extracted from a model, or it could just be some trajectory planning method. And in fact, in this work, I'm going to just assume I have some trajectory planning happening, and that gives me a desired trajectory of either end effect positions or joint positions. And then I would say that currently most of the robot learning community then just says, okay, let's send these desired end effector or joint positions to the robot, and then hopefully the robot achieves these desired actions. And what I'm going to show you right now is exactly such an example, and it's really hard to see this right now, but there is a plan here in green that was planned, and now you see the robot executing this plan, and it perfectly tracks the plan. Just to show you again, there's a green line that is being planned, and this is step by step. The actions are sent to the robot and are being executed, and everything works perfectly. But now, when we do pick up an object, something different happens. We are in the same configuration. We plan exactly the same plan that you see here, but as it tries to execute these actions, the arm drops. And this really is because we've now simulated having this object in hand, which has a significant mass, really, and there's nothing compensating for this mass. So just to get into this a bit more, what's happening is that there is actually a controller that takes our desired action commands, let's say joint positions here, and that controller computes torques or efforts that are then sent to the robot. And those torques and efforts are basically what define the actual behavior on the robot. And what is happening now when you pick up the robot is the object is that the controller is not aware of this object, and so it's not compensating for it. So it's not increasing the amount of torques necessary to move this object, and that's why we get bad tracking. So of course, we can adapt this controller to compensate for this. And just to prime your mind now, here is try to think about what this means for all these objects, right? So what do we do? And I'm gonna just discuss two questions here right now. There are more choices that are to be made, but these are some of the, I think these are two main questions that I think about. So I just want to quickly discuss them. One thing is, okay, we just discussed that we kind of need to adapt this procedure to compensate for the object that we're picking up. And we actually have a choice here. We can either update the high-level policy or we can update the controller. And in this work, and most of my, really all of my prior work is let's keep the policy and we update the controller. And in fact, there is some old work from Chris Atkinson and Hollerbach that shows that actually humans maintain the path even when they have varying loads. And so this indicates that that we have an internal model that allows us to compensate for different loads that we're picking up. And the second question that I think about is a lot actually is, now that we've decided we want to somehow allow the controller to learn about these objects and how to compensate for them, do we try to learn this controller or this model in the controller to compensate for each possible object? Or do we learn how to adapt the controller? And let's go back to this picture here. What I think about when I see this picture, what I see is that I really have a hard time predicting the masses of all of these objects. And I'm zeroing in on the mass because it's a big factor of how much we have to compensate. There are other inertial parameters that influence, what kind of torques we have to send. But it's just really hard. Sometimes we don't even see the content of the object and we wouldn't be able to know, right? Even if we include vision into our system. So this kind of insight makes me believe that it seems really impossible to learn a model for each rigid body or non-rigid body, especially if we don't have full observability. But it does seem feasible to learn how to correct for deviations from expected/desired sensor signals. And that's kind of a handful what I've just said here. So I'm just gonna repeat this one more time. What I think is feasible is to use the sensing of the robot and then to learn how to correct from the deviations of what we wanted to achieve, like a desired joint angle, and what we've actually achieved. And again, in fact, this is something that we have observed in humans as well. So humans seem to learn a memory of errors, which helps them adapt to previously experienced errors faster in the future. And it's really this kind of notion that has inspired how I think about meta-learning for robotics and has inspired some of my previous and current work. Okay, so how do we learn to adapt to errors due to changing dynamics for such pick-and-place tasks? So now I'm going to get very concrete. Before we go to the meta-learning part, let's first talk about how do we adapt the model in the controller online. Just to quickly recap, we have some policy here. It's a motion plan that predicts desired joint positions. Then these desired joint positions are converted by the controller into torques that are then sent to the robot. And really what the controller takes in is not only the desired position and velocity, it also takes in the current joint position and velocity. And then it predicts a torque for each joint. And what often happens when we do parameter identification on robots is that we collect a data set. So here we see the robot moving in some sine motion. So each joint is moving along a sine curve. And we do this usually for different frequencies. We collect the data for this, and then we fit the parameters. That would be the parameter identification way. And what we're doing is we collect these tuples at each time step of the joint angle theta, the joint velocity theta dot, the torque that we apply. So we use this controller to actually compute the torque that we apply. We send this torque. Then at the next time step, we observe what the next joint state and velocity is, joint position and joint velocity is. And what we're going to do to actually learn these parameters is to pretend that this next joint state was our desired joint state, because that's going to perfectly match what our torque is, right? This tuple is exactly describing the real dynamics of our system. So we're going to pretend that this was our desired action, because this matches with the torque that we send. And then, so the input, when we online adapt our controller parameters W, are the current joint position and velocity, and then the desired is the next position velocity. And we're going to predict the torque, and we know what torque we actually applied, and then we compute a loss based on that, and we back propagate that error. Oops. Yeah, so back pop. Okay. So this was the description of just online adapting. Well, it's the same procedure for offline or online adapting, but this is how also I've used it in the past for online adapting. And here's what I've learned to be some of the main challenges in like online adaptation of these inverse dynamics models. One of them is really computational efficiency. And what that means is these control loops usually run at a relatively high frequency of 500 Hertz or 1000 Hertz. And you can't really perform that many gradient steps. And each gradient step has to be fast. And then second, data efficiency. And that just means we do want to adapt relatively fast. So with few observations. And then the third one is safety. And to be honest, this one is still a tough one for me to crack. And I'm not going to really talk about it that much today. Okay, so learning loss functions, which is what we're going to do next, can help with computational efficiency, because hopefully a learned loss helps us adapt the model with fewer gradient steps. But also hopefully it helps us with adapting the model with less observations, so faster. So both of them. Okay, so when we learn loss functions, we have two phases as all meta training approaches. And the first phase is going to train the loss function. And then the second phase, we're going to use the loss function to adapt dynamics models online. So how do we train this loss function? Just to bring this picture back here of our controller that takes in the current and desired joint position and velocity, and it predicts the torque, and we know what torque we actually applied. We compute a loss, and then we adapt the controller parameters omega. This loss function usually is either a mean squared error or a normalized mean squared error. This is a function approximation problem. Now I'm going to talk about how we learned this loss function. Before I talk about, no, actually, I'm going to first say how we learned. We use just a bilevel optimization framework here to optimize these loss parameters theta. And this is also the same framework that MAML uses. It's just MAML optimizes the parameters omega, while we optimize the loss function parameters phi here. We use a library Higher to compute the metagradients. I'm not going to go into details about this, but you can look at the references I'm listing at the end to find details. And then in the meta train, then also important is that our meta train phase is actually self-supervised, so we don't really need this task family. We don't need to design task families. We're just going to move our robot along some sign motion paths, and that's the data we use to meta learn. That's all we need. For more details, you can look at our recent paper that we put on arXiv. Okay, so now what I just wanted to say before is that we also need to specify the loss function representation, right? And what we're proposing here is that we use actually a fairly structured loss function representation in this paper. And just to walk you through it, it almost looks like a mean squared error, right? J is the number of joints that we have, and this is tau. Tau hat J is the prediction of the torque per joint. We're squaring that error, and now we're weighting it by a function that is a function of the state. And that function can be the function of the full state of all joints or just of the J's joint. And just to give you some intuition of why we thought this would be useful, we're really saying that we should penalize errors dependent on where the arm is in the state space. And there are some very simple cases of like, there are these configurations that the arm can't actually move any further as along a certain joint, and then it creates very different errors than if you're completely free to move. There's also often around this 0 degree, and when we move slowly, we have something like static friction, which just means we need a little bit more torque to get across that 0 degree threshold. And so it's kind of really dependent on the state how much we should penalize an error or not, when it comes to learning these low-level dynamics at least. And so the baselines that we compare to is just the standard mean squared error. Then we also compare to just learning a neural network that takes in the torque and the predicted torque. And then we're also going to compare to a very similar one, the state-dependent loss that we propose here. We just compute a constant weight. We learn a constant weight per joint, so it's not going to vary across the state. And in these neural network losses is something that we proposed initially to do, and here basically we are trying to get towards losses that are more interpretable but also easier to learn. Okay, and then at meta test time, we want to use this learned loss to hopefully adapt the dynamics such that the robot can track this path very well. Okay, so to recap, the meta training data collection is a happens on this sine motion task, where we just define some sine motion per joint at different frequencies. This happens either in simulation or in hardware. And then at the meta test time, we perform a pick and place task, and we just want to learn a neural net to fit the dynamics online. And what I really want to highlight here is that we are not having the object in hand during the meta-train data collection. We're just using the arm. When we collect the data on hardware, we do have the gripper attached, which changes the dynamics slightly as well. Our KUKA arm is gravity compensated, so the torques that we really need to correct for are just the non-gravity compensation torques and any torques required to offset that milk carton, which is about 800 grams here, so it's almost full. Yes, and just to also be very clear, the results I'm showing next are just trying to fit the dynamics online as fast as possible, but we're not actually applying the torques because that creates some safety concerns, which we're still figuring out. Okay, before I go to the pick and place task, the really exciting part, I want to just show how the meta training phase works for these different losses that we are comparing. So during the meta training time, what we're doing is we're learning this loss function, and at each meta epoch, we're then testing this loss function on some fitting task. And that's the loss that we're recording here. So the straight line here is the MSE loss. This one doesn't change because there's nothing to be learned, so it's just constant across all meta training phase. The blue line is the neural network loss. The green line is the structured loss that is not state dependent. And then the purple line is the loss that we propose here, which is the state dependent structured loss. And as with our good machine learning papers, our proposed loss outperforms the other losses. And we do this, so we're training on some meta training data, and we also have some held out data of the sine motion task that we use to test for generalization, at least on the sine motion task. And as you see, these look very similar. So that seems to work well. And just to show you some optimization traces with these losses then, here you see them. So this is after meta training has commenced here, after 300 meta training epochs, we execute this learned loss on training a dynamics model on some data for 100 training iterations. And here you see that the state-dependent loss outperforms the other losses. And these results are averaged across 5 seeds, where the seeds affect the dynamics model initialization as well as the loss model initialization. Okay, so now we come to the exciting part. Here's our pick and place task, which we decomposed into 5 primitives. We are trying to reach the milk carton, lift it, then move over, place it down on the table, and then retract the arm. What we do is, as we're moving, we are recording the errors that we're making, and we use it to adapt a dynamics model that is randomly initialized here at the beginning, and this is a plot as a function of time. And what you see here on the y-axis is the mean squared error made for each dynamics model that we fit with different loss functions. And you see these spikes here because the torque, the amount of torque that we need during each movement fluctuates. And so that's exactly what the model needs to adapt to. And so if it doesn't adapt fast enough, that's how the error spikes basically. And the state dependent loss does really well on just keeping the error low all the time, right? It doesn't fluctuate at all. It outperforms all the other losses, including the mean squared error loss, with higher learning rates than what we use during training times. And yeah, that's just really exciting. And we see this for all, we really see this for all movement phases here. The dynamics models trained with the state-dependent losses outperform all the other dynamics models that were trained with other losses. And so one thing I was really curious about is whether we also get the benefit from training the loss function in simulation and then applying that loss on the real pick and place task, right? So these results are learned loss function on real data, on the real sign motion task, and then applied on the real data for the pick and place task. And now we're going to look at results for the loss function learned in simulation on simulation sign motion data, and then applied to the real pick and place task. And sadly, here the results look not that great. What we do see is they do work, these losses, but we actually don't see, so first of all, we don't see the state-dependent loss outperforming any of the other losses. In fact, I believe it's the structured loss, the simple structured loss that performs the best. And thinking about it, after analyzing the results, it's actually not that surprising because the simulation really doesn't simulate the state-dependent things like stiction, for example. So it can't really learn about it when trained in simulation. It can only learn about it when trained on real hardware data. And so this is exactly what we see. And it kind of makes sense now. Okay. So these were some results for how meta learning can help us adapt dynamics models online in a very computational and data efficient manner. And the takeaway really is here, I have two main takeaways from this work so far, is that actually learning state-dependent losses can outperform what I call now domain invariant standard losses. So these domain invariant losses that have no structural bias from the domain baked in. And also very exciting is that these learned losses can actually transfer to out-of-distribution meta-test scenarios, right? That's exactly what we showed by training on the sign motion task, but testing on the pick and place with an object with significant mass. And that was not an obvious one for me, but it was great to see that it actually works. Okay, that was it for today. Thank you. And these are all the collaborators that have contributed to this work. I'm highlighting two papers here that we submitted last in this year about this work. Thank you for your attention. Bye.